Hello, thank you very much for joining me for this presentation. And I hope that most of you chose this talk because, well, just like me, you believe that very often the software that we all write, well, is simply too hard and too complex to understand. And so the purpose of this presentation is to answer a question whether we can maybe find some sort of visual aid that will help us to navigate the Elixir systems we write, maintain, modify, and need to understand. And I believe it goes without saying that one picture can tell more than 1,000 words. After all, our lives would have been much harder if it wasn't for all sort of maps, like road maps or hiking maps. So let's just check and see if we can maybe draw a map for Elixir systems. There's one thing that needs clarification though before we move on. That's what do we actually mean by complexity that appeared in the title of this presentation. So the first thing that might come to mind, well, especially if you have attended computer science classes and had to deal with all of the whiteboard exercises related to this, is computational complexity. So relax, we're not going to be doing any exercises today. We're not going to talk about that kind of complexity. Rather, we're going to consider complexity as defined in this already classic paper, Out of the Tar Pit by Ben Moseley and Peter Marks. Well, this paper basically addresses software complexity throughout all of its almost 70 pages. It's a really great read, and the authors are talking about the type of complexity that make large systems hard to understand, and it's this, so having hard time with understanding the systems, that causes us to expend huge resources in creating and maintaining such systems. And just to give you a little bit of background how I got interested in this topic, and especially the visual part of it. So last year, when I was preparing for this talk at Code Elixir London, the main argument of this talk was that the software that we build and that has appropriate layers of abstraction is much easier to understand and maintain than a system that does not have those layers of abstractions. And since it was a conference, I had to show some slides. So I just decided that I will kind of graphically show the structure on the graph that represents dependencies between modules. So kind of, quote, graphically prove, unquote, that a system with a structure looks much nicer than one without the structure. And as it turned out, it was much easier said than done. And unfortunately, the problem with all of the classical graphs or tree-like graphs is that even if we have a simple project that has a lot of structure, they very quickly start to look something like this. And unless you give some hints to the drawing software, like which nodes should be close to one another, you most likely won't get anything meaningful back. But giving those hints to the drawing software is kind of already defeats the purpose of drawing such graphs automatically. And without providing this additional information, well, simply all projects look like mess, like this, which was a simple project, believe me. So I was looking for something that would work better, at least for Elixir projects, and it was not a trivial task. Until eventually, when I was looking through a gallery of D3 JavaScript visualizations, I came across something that looked like this. It really caught my eye, but well, not exactly because what it was representing, at least not yet at the time, but because it resembled me one thing, this thing. So when I was at elementary school, I had a really interesting subject called design and technology. I'm not sure if that's a subject taught outside of Poland, or even if it's still taught in Poland because it was 20 years ago. But that was a really interesting subject at school when they taught us, well, how to use a screwdriver, how to ride a bike, or how to even make a sandwich. And we also were doing something like this. So basically, you hammer those nails into a piece of wood, then you use the threads and create a pattern like this. And it was called a peacock's eye. Mine was actually a little bit different from that. It actually formed a circle, but I was not able to find a picture from 20 years ago. I just found that online. So it resembled me this thing. And so when I look closer at this graph, it turned out it's exactly what I was looking for, because it represents a software project structure. And this kind of graph is called hierarchical edge bundling. And I'm going to explain in just a little while exactly how it works. For now, I just wanted to point out that, well, it looks like, sadly, this method of visualizing software projects did not get a lot of traction. So I was trying to Google the name and so on, and it was very hard to find any other examples than this. And this example, by the way, has been implemented by Mike Bostock, who's also a main author of the D3 library. And what you see here represents a hierarchy of a project in ActionScript called Flare. And ActionScript heavily relies on the fact that classes that are implementing certain subsets of functionality live close by in the directory structure, right? And that's exactly what we have in Elixir as well, where we have module naming convention that introduces some hierarchy into the project. And obviously that naming convention is not enforced in any way by the compiler, and there are also some certain differences when we compare it to ActionScript. But we can still utilize these methods and do similar thing for Elixir. So now let's see how this method of graphing works with Elixir. So let's say we have 26 modules from A to Z. So as a first step, we put them on the perimeter, sorted alphabetically. That's a very important part, sorted alphabetically. So we hammer those nails on the piece of wood. And then let's say we have a module A, and module A is calling a function from module B. So we can say that module A is aware of module B's existence in some way, right? So we draw an edge from A to B. And to be precise, we also would have drawn the same edge if A either created or matched on a struct that's defined in B. So then function module B is calling a function from the module C. So we draw an edge from B to C. And then we continue doing so until we get to the last module, module Z, and that's calling a function from A again. And so we have an edge between each pair of adjacent modules. And that kind of ring is really the simplest possible graph you can generate in this method. We can say it's a lower bound. And perhaps I lied a little bit to you just a while ago when we had those 26 nodes without any edges. Because in fact, if a node is not connected to any other node with an edge, it simply won't be drawn on the graph. So that's what we're seeing here. If we have 26 modules, it's the simplest possible graph that we can draw, assuming that all the modules are used. So now let's change the implementation a little bit at the reverse relationship. So now module A calls not only one module forward in this ring in the clockwise direction, but also one in the anti-clockwise direction, right? So module A calls B and Z. Module B would call A and C, C would call B and D, and so on, right? So what does it generate? Well, exactly the same graph as previously. So one caveat of this method is this graph is undirected. So we're not really able to see any cycles. And the cycles in the project also might indicate that we have some problems with complexity in our project, right? At least these graphs are not represented for now. The generation can definitely be improved to support this, but as of today, cycles are not visible. So let's do one more thing with those A to Z modules. Let's just say now that every module is calling every other module. So module A is calling modules A to Z, module B is calling modules A to Z, C is calling modules A to Z, and so on. And what do we get when we generate a graph from this? We get this, which you must admit looks pretty cool, but from the complexity perspective is actually the worst case scenario. because we literally can make our system worse, right, than every module being aware of every other module in the system. And this graph has approximately, 26 squared connections, edges on the graph. And if we were to understand the relationships between all of those modules in that code, that's exactly how many links we would need to explore, right? So that's almost 700. But 26 modules is not really a lot for a project, right? Anyway, this graph is kind of our upper bound. And this actually looks like this piece of art I showed you before that I did when I was 10. We know how hierarchical edge bundling graphs are created. So let's take a look at some real project now. Let's start with the simplest possible one, freshly generated Phoenix project. So if we generate a Phoenix with mix Phoenix new command, this is what we get. We can see the modules that have been generated by the command. So we can see, for example, router or the default page controller. And we kind of expected that there won't be a lot to see here because, this is an empty project after all, right? So it just has these files generated by the generator. But we can go a little bit deeper, and we can also include modules from the project's dependencies on the graph and see how they are used by the project source modules. So if we do that, we get something like this. And this is actually hierarchical edge bundling in all its glory, because here you can see that modules from one directory or from one dependency are actually next to each other. So here we have our all empty Phoenix project source modules. Starts with fresh Phoenix. And one thing to note is that even though we did not add any new files in the meantime between generating the graph without dependencies and with dependencies, we now can see more modules than we have seen previously. And if you remember that A to Z example, for instance, the fresh Phoenix web.telemetry was not drawn on this graph without dependencies because its only edge goes to telemetry.metrics. And that's a dependency. So we didn't draw a dependency module, so we also didn't draw the fresh Phoenix web.telemetry module when we were not drawing dependencies. But let's just see other dependencies and confirm that, I guess we can see that, but just to confirm that all the dependencies are have the modules adjacent to one another, like getText, Phoenix, it's here, plug, there's telemetry with one module, and finally Ecto. So I think we now understand what hierarchical edge bundling graphs are, what properties they have, how to draw them. So let's take a look at the graphs of some real projects and see what we can learn from those projects. So we're going to cover the Elixir Big Three. Let's start with Ecto. This is Ecto. And we can see that Ecto query part seems to have most edges and the nodes as well. So a lot of is going on here. But actually, I didn't want to show you Ecto graph to analyze this architecture. I just wanted to show you what will happen if we add one level of the dependency modules. So this is what happens. And in fact, this did not change a lot because just these two new modules appeared. So telemetry and Erlang module, because it starts with lowercase, and decimal, right? And if we go one more level deeper with the dependencies, we just see a couple of more modules. So these are modules that are called from the first level dependencies, right? So they were brought here by telemetry and the decimal, but we just see like 3 or 4 of them. In conclusion that we can draw from this is that, Ecto seems to be pretty self-contained library. It does not have many dependencies. And that mixexs from Ecto confirms that, basically, right? So we have only 3 dependencies, really. Xdoc is just used to generate documentation. But hold on, we actually didn't see JSON on the graph, did we? Well, here's another caveat to this method, at least for today. Only the static code will be analyzed when the relationships between modules are extracted. And since JSON is not called anywhere in the active static code, it will happen, it might happen in the runtime. We won't know that an edge should be drawn until, well, some more dynamic analysis is added. So it's not here yet, right? That was Ecto. Let's take a look at the second one, Phoenix. And when we see the Phoenix graph generated without any dependencies, this looks like a fairly small project. And it looks like the most interesting stuff actually happens in those mixed tasks, maybe. But let's see what happens if we just add one more level of dependencies. We see much more stuff going on, and this makes much more sense. The reason for that is pretty simple, because Phoenix project is just organized slightly differently, right? It's split into several sub-projects like Phoenix PubSub, Phoenix HTML, and don't forget that most of the HTTP connection logic actually happens in Ply. If we add one more level of dependencies, we're actually able to confirm that indeed there is some HTTP server used, as we can see Cowboy and Ranch modules here. So one thing we can learn from this is that, well, given a project, we can pretty quickly check out not only what the dependencies the project is using, because, well, that's something that we can already do by looking at mix.exs, but also where exactly and how extensively they are used in the project, right? So now let's just take a look at the last of the big three, Absinthe. Well, this is a big project, right? Definitely the most complex from the projects we have seen so far, and both in terms of, of the number of modules and the number of edges between them, and just keep in mind this has no dependencies. This is zero dependencies. Every module starts with absence. I actually haven't thought of it before, but would be actually a very interesting exercise to compare this graph to, I'm not sure how, but somehow to the GraphQL spec, like how many of these connections here are actually coming from the complexity of GraphQL. Anyway, what I wanted to bring your attention to is how this tool could be used. So far, we've been looking at the projects that will, let's say we don't know much about. However, I guess there might be a couple of contributors out there in the audience, but like in general, let's say that we don't really know the architecture, what the architecture of this application is. And so I had a chance to work as a consultant for 7 years, and very often was tasked with a project that I had to jump into very quickly. Very often the expectations from the customers were that I'd be able to make really significant improvements in a really short period of time. And that's not an easy task, especially since, in those more complex projects, it might take 2 or 3 months to even start understanding the business domain that an organization is dealing with. So creating those graphs can be very helpful if we don't know what the system is doing, and we need this sort of a map that will help us navigate through the project when we're in the process of learning what it's doing. And Steve Jobs used to say that a characteristic of being a smart person is being able to zoom out and look at a problem from a high level. Well, this will definitely help you to be just a little bit more smart next time you need to deal with a complex system that you will have no idea how it works. And just looking again at the absent example, right? Let's say you have zero knowledge of absence, you clone the repository, you draw a graph, and in order to being able to say, yes, I do understand 100% of the absent code base, you would basically need to understand what all of these edges here mean, right? In what way certain modules are aware of the existence of the other modules. And that can be a pretty daunting task. So with a map like that, you can say, what modules seem to be the most important, where's the most stuff going on, and where it makes sense to start your journey in this project. Since we covered the path where we don't know what the visualized system is doing, let's just do the opposite and see how hierarchical edge bundling can help us with the system that we do know and do understand. So let me show you another graph of a project that I had a chance to see. And so this project was facing two problems, despite using both absence and Phoenix together with the context. And first of all, for some reason, all the data models have been moved out of the context and stored in the common directory. So that's a group of nodes here. And secondly, contexts have been split not by a business subdomain, but like, for example, identity and access management, inventory, customers, things like that, but rather by entities like account, session, so specific schemas. And this leads to a situation where we have sort of, after seeing this graph, have an impression that, well, there are no really any logical parts here. And every module could technically call every other module. And some parts of this code base are even dead. So let me show you now how a graph for a slightly better structured project would look like. There's another project I had a chance to see, and well, hopefully you already see that there's more structure than the previous one. And it's also Phoenix in absence application, right? And all the modules related to the API layer, so all the controllers, all the resolvers are in the top right corner on the graph here. And obviously there are some connections going to the rest of the application, because otherwise that would mean that they were not used. But the boundary here is pretty clear, right? This already tells us it is possible to create a project where actual business logic is decoupled from the API layer. So just to make things easier in the next couple of minutes, let me remove these connections for now. So this is just the business logic, no API layer. And we can see that there are a couple of strongly connected cluster of nodes, around 5 or 6 of them here, that sporadically connect to other clusters. So these exactly are contexts. They're split by a business subdomain. Single business subdomain is fully responsible for it, like, you know, customers, for example. If it was some sort of hotel booking application, we also have something like bookings or inventory. On the right-hand side, although, we can see a couple of hot modules here, but these modules are just modules that are commonly used across the project. Like, for example, a module that represents, like a struct that represents an error. Well, having that kind of hot module already suggests that it might be worth extracting a separate library. But either way, if our, you know, links dependencies between modules in the projects look like that, this probably means we're using context properly. And since they properly abstract parts of the domain, and thanks to the minimal number of cross-context connections, you can later easily extract them and deploy separately if such a need arises. And the secret behind a much nicer looking graph in this project is layered architecture, where we split responsibilities between, in this case, services models and data access modules. So let me show you an example. Well, it's not really important what the code exactly is doing. It's just here to show you the structure where specific modules are. So this is a model, right? It's represented by a module living in the customer's context. There is a model directory, and finally there's a customer, the struct called customer, right? Well, in this case, it's defined as a pure Elixir struct, can be active schema as well. Doesn't really matter. There's some ID, there's some name, and there's some tier. We don't really care about it. We just at the moment care, you know, where in the project, in the project hierarchy it lives. There's some constructor that we can create a struct from some parameters or out. And there's some business operation. We can upgrade a customer to a higher tier. Doesn't really matter at this point. And if we draw just the models from our project, this is what we get. And there's clearly the distinction between the contexts now. And we can see that some of them have more models than the others. And this suggests that they're just more complex subdomains. And we still see those hot modules on the right-hand side, the one that I talked about the error module, because they were classified as models, because they're pure structs basically, right? But besides that part on the right-hand side, there are no cross-context links at all. And if we need to keep the state of these modules in the database, we're going to persist it through another layer that's responsible for all the interactions with the infrastructure we depend on. So that's this data access layer that I showed. So that can be not only database, it could be emails, push notifications, anything external to a service, really. So again, just to show you the structure, again, we're in the customer's context, but then we're in the DA directory. And the customer's module is responsible for all the data access operations related to the customer. So for example, here we have a get function. We get a customer based on the ID. It might be implemented either in pure SQL, actor repo calls, calling MongoDB, doesn't really matter. What matters is that this module is just fully responsible for talking to the database. So not just fetching, also updating, deleting, creating, everything that requires talking to the database. And if we visualize those data access modules in our project, this is what we'll get. And again, we can see that there are no cross-context links again, with an exception of this error model on the right and one hot module at the bottom, which is actually our repository. Because yes, that was using actor repo, not pure SQL. And we can also notice that some contexts are, more I/O heavy. There's more going on. Maybe responsible for notifications at the bottom. They are different in size, basically. Anyway, in order to get the same graph that we've seen previously, before I start to break down the project, we're only missing one thing, something that will actually make use of the business model and all this data access. And implement actual use cases. So that's in this pattern, it's called services. So again, we'll in the customer's context, this time in the service directory, we have a customer service, and the upgrade function is something that exposes, represents an actual use case that we want to expose from our context. And this module really, and those functions, those public functions from here, are really the only entry points to the context. So these functions will be called by either microcontrollers, apps and resolvers, or another context. And if we add, if we draw those services in this blue, light blue, to the graph, we finally get some cross-context connections, cross-context interactions. And if you remember, when we generate this graph, it's non-directional. But even if it was directed, then we would see that there are no cycles here. Because, well, actually in this pattern that was used here, to generalize, we would see that the following relationships between modules apply. So services known about models and DA dependencies. DA knows only about models and doesn't know anything about services, and models knows only about other models, basically. So I'm not saying this is the best project structure out there, but maintaining some kind of layer structure helps organize code, actually help organize code a lot better in this case, and believe the graph, the modular relationship graph, is actually proving it. We could also introduce some other structure, like maybe the one that was suggested in the Out of the Carpet paper, or clean code stuff, or the Onion architecture. Doesn't really matter. All that kind of stuff should give us similar results. So now we also know how we could use these graphs if we generated them for a system that we know what it's doing. So we already have some assumptions about the architecture of the system. From high level, we know how it should look like, right? We can just generate a graph, take a look at it, and see if indeed is reflected on the graph. So, okay, now you're probably wondering, it's all cool, but how do I generate the graph for my project? And the answer is here. So there is this small project on GitHub, welliron/graph, which is graph in Polish. To be frank, this project was developed purely in the conference-driven development methodology. So it wasn't for the talk today, but I would have never created it probably. So, there might be some issues like bad error handling and something like that, but it should work for your project as well. If it doesn't, just please let me know via GitHub issues. And I know that in the abstract of the talk, I promise that there will be a service that you can use to generate a graph for your open source project. Well, there's no service, but there's something better, so you can generate a graph for your customer's proprietary code. Hold on, there's a buzzword alert, a Docker image. So it's all in the README, but if you just clone the repo, like Ecto in this case, and just run the Docker with a couple of options like mic steps depth that I shown, whether to include built-in functions or not. I can also change the color of an edge. We should see just the graph that you have seen on the previous slides. If you don't want to use Docker image, that's completely fine. There's also a script. The only dependency really is Node.js, because you need to use D3 to generate it. And if you're wondering what well iron is, well, that's a small website that Simon Zelazny and myself are running. We create a couple of small libraries that we are using in our daily work. We borrow some interesting concepts from ideas from other functional languages, like parsing input, error handling, things like that. And on the website will-iron.com, we write some posts trying to convince you why it makes sense to use those libraries. I still believe I owe you one thing. So what do these graphs actually tell us about complexity? Again, so here are two graphs. On the left-hand side, we have the graph from a project with the layered architecture. On the right-hand side, a project without any real structure. And overall, the project is less complex the less edges there are on the graph. Well, simply because we need to understand much less relationships between different places in the code. So overall, we should be minimizing the number of edges, right? And most of those edges that we already have should concentrate in these groups of nodes that are close to each other. And well, this way they will create grid abstractions with really small number of entry points. And the number of edges in the center part of the graph should remain as small as possible. So this cross abstraction, cross context connection should be kept to minimum, right? And it's obviously not possible to keep that middle part empty, because that would mean that we have dead code or dealing with this trivial A to Z modules example, perhaps. But we should at least be able to trace which modules are connected by an edge, right? And so there's no universal way of saying, yes, this graph represents a non-complex software system without knowing more about what it's doing. But just like we're able to, to walk into a room and quickly assess if it's tidy or not, we can also quickly generate a graph and assess aesthetics of the architecture of a project by looking at this hierarchical edge bounding graph. And if you haven't written down the repo address yet, here it is again. Thank you very much and stay safe.
Thank you, Rafał. So we have just over 5 minutes for some questions. I take it you can all hear me. Yeah, okay, great. So let's work through those. I'll ask the person who asked the question to sort of ask that on their own. So please unmute yourselves. So Ihor, you can go first. Okay, so let me just let me read that out then. So Rafał, essentially now that we can visualize the complexity, Ihor is asking, what does it give us? What can we do with it in terms of using it in a practical way?
Well, so depending there are these two paths I kind of tried to show, right? Depending what use case we have. Really, we can use it for both systems we don't know what they're doing, and we need to learn what they're doing quickly. That can help us trying to understand, it's like a map basically, seeing what talks to what, which modules talks to what. If we generate dependencies, also we can then see, okay, these dependencies are used from this part of the system. These dependencies are used from this part of the system, for instance. On the other hand, if we know what the system is doing, we have some assumptions, like, on the pen and paper, during whiteboard discussions, we said this system will have those layers. Like, we keep this part of the system, like customers handling in this context. We keep database, we talk to the database in this part of the system. That's what we do when we design the system on the whiteboard with pen and paper. This can show us if we, maintain those ideas also when we write the code. I guess that's my answer. At least that's okay. That's how I'm using this.
Great. So one more question. Nicholas, are you available to unmute yourself and ask? Okay, I'm going to read this one out too. So Rafał, this one is about, basically, I think what it's trying to get at is we can use things like bounded context from DDD, which is used to sort of basically deal with complexity or do abstraction properly. And have you analyzed systems or projects that use that kind of approach? And have you noticed any differences?
So yes, actually the good example I've shown, it's the idea here was the project from the beginning was trying to approach complexity the DDD way, although it's so I believe it's visible in the structure, although it wasn't always true, because it was a real system. Some shortcuts happened during the development. Some things ended up in the wrong context. That's why I pointed out that there were not ideal things there as well, right? But the overall structure, if we just take a quick look at it, right? Well, obviously those projects didn't have module names. That was obfuscated, but if the names were there, that would be obvious that this part of the system is responsible for this department of the organization, let's say. The other context is responsible for the other part of the system. So yes, actually, the good example was trying to follow DDD, although that was not the case in 100% of the cases.